So I think. Okay, today we will continue with the colloquium program, and today we have an invited speaker, which is an honor for me to introduce, is Dr. Denis Sivers. Dr. Sivers did his undergraduate studies at the MIT, and then he went to California, and he obtained his PhD from the University of California at Berkeley, and he worked there with Jeff Shaw. And after that, he did several postdoc research positions. He did some at Argonne and also at SLAC. Then he went to the Rutherford lab in England. And then he came back to the US, and he was at Argonne as a research staff, as a physicist. Then he went and worked in real estate. He's been working in this project as well, and he's currently associated also with the Proton Institute and the University of Michigan. And we are very happy to have him here and to discuss about the proton structure and the stellar genome. So thank you.
It's a pleasure to be able to discuss this topic with this audience. And in 1929, Paul Dirac made a very famous statement that's written there. And basically that statement carried on to say that what needs to be done to study chemistry in solid state physics and other areas is to work out new mathematical techniques that will expand what's known about the fundamentals of quantum theory. In 2007, the Nuclear Physics Advisory Board delivered a very strong statement that updates Dirac's 1929 pronouncement, and I'm going to read that to you. I'm not going to write it down because I don't think it's worthy of being put on the same level as Dirac's statement, but it's one of these pronouncements. A central goal of the DOE Office of Nuclear Physics is to understand the structure and properties of protons and neutrons, and ultimately of atomic nuclei in terms of the quarks and gluons of QCD. So that's a stated goal of the DOE in funding new projects in nuclear physics. And it means that the DOE has accepted that the standard model, including QCD as the generator of the strong nuclear force, has been accepted. But one thing that isn't true are the mathematical techniques to exploit that at the level of nuclear physics, just like Dirac's position in 1929. So I want to emphasize that this isn't directly a talk about stellar evolution or even about the various progression of fusion processes that are involved. But it is trying to take seriously the fact that once we get a better understanding of the structure of the proton and the emergent phenomena and non-local aspects of QCD, we will have better tools to use in nuclear physics to discuss the processes involved. Now, QCD is based on the observation by Gross, Wilczek, and Politzer that won them the Nobel Prize that QCD is an asymptotically free theory. So when we talk about scattering at large momentum scales and hence small distances, that theory can be understood as a perturbation theory. So we understand QCD in terms of a theory of quarks and gluons interacting with large momentum scales. The fact that we don't understand QCD in total has been remarked And it has been codified in terms of the Clay Mathematical Institute, one of the 7 Millennial Prize problems in mathematics is to prove that QCD is a confining theory. And so if you have an idea how to do that, you could write it up and go present it and claim your $1 million. That prize, there were 7 questions that were posed. This one was posed in an official paper by Arthur Jaffrey and Edward Witten. And there have been comments on that proposal, but nobody has made a serious attempt to claim the prize. Important in this is that the mass of the U quark and the mass of the D quark are known experimentally, and the values that are shown there mean that for a proton, only 7 MeV of the protons, 7 or 8 MeV of the proton's 938 MeV mass are made up of the quark masses. So less than 2% of the mass of the proton is understood in terms of the Higgs couplings of these particles. The rest is dynamically generated in some way. And so right there, that's a clue to that binding energy curve that I showed in the first slide, because all of that 930 MeV that's binding energy inside the proton is available to be shared when the protons and neutrons get together to form more composite systems. And so how the structure of protons and neutrons change as they go into nuclei is a study of experiments. And one of the things that's often plotted is the ratio of the structure function for proton deep inelastic scattering and deep inelastic scattering a proton off of in a nucleus. And the curve is where this is Bjorkane x, and this is x equals 1, and there's a Fermi motion tail, and then there's a deficit for a while. And this shows that the structure of protons does change when they're bound. Nobody has done the same thing for the gluons and all of the quarks and antiquarks to do the sum to see that it ends up to the binding energy, but it probably does. But so we know right off the bat that this idea that the mass of protons and neutrons is dynamically generated makes sense. And there are several other tools that have been used. Here's the official presentation of the problem. They use a slightly different notation than I do, and they talk about the proof of confinement in terms of the generation of a mass gap. And they tie it to chiral symmetry breaking, but we believe that we're much farther along in understanding the origins of chiral symmetry breaking than we are of understanding the total package of confinement and chiral symmetry breaking together. The main part of the development since the problem was posed in year 2000 has been studies of the spectrum of hadrons as found in lattice simulations of QCD. And the fact that the lattice has something to say about confinement was projected very early by Ken Wilson in one of his fundamental papers. He showed that in a strong coupling theory, the area law for Wilson, so-called Wilson loop, is equivalent to having a linear potential between two charged sources. And so in the world where you have heavy, massive quarks separated by a long distance, the energy would grow linearly with that. Of course, that doesn't deal with the effect of the light quarks, the loops, the virtual loops that would break that, but it is certainly a necessary condition in order to have confinement. If that weren't true, we wouldn't believe that it could be maintained in the case of a light quark. People have used effective field theories, also invented by Wilson, to discuss what happens when you put a light quark and a heavy quark together. That's called the massive quark effective field theory. They've also done soft collinear effective field theories where you use perturbation theory at large distance and you model the behavior for soft and collinear parts of phase space. And there are chiral effective field theories, which is a theory of the interaction of pions and nucleons, which has been studied in great detail to higher orders and is relevant for the soft scattering of pions off of nuclei and nucleons. There's also been extensive development in various equations that resum diagrams, and in particular you can use Schwinger-Dyson equations with boundary conditions that introduce an effective parameter like an effective field theory and talk about the analytic properties of dressed propagators. And the Schwinger-Dyson equation is basically the idea that the dressed propagator for a fermion can be written, there's a in terms of two dressed vertices, and then this leads to a nonlinear integral equation that can be solved recursively. And these equations have been studied, and it's been shown that you can generate a mass gap using those equations. But again, this is additional evidence, but it's not yet sufficient to claim that we can prove that QCD is a confining theory, because we haven't put this thing inside a hadron. We've only talked about it in terms of its properties. And then the final thing, and which is something that Professor Ralston and I worked I'll stay with that, worked at in Argonne in the 80s are basically the non-abelian Maxwell's equations of SU2, but they can be generalized to SU3, and they have some help to understand the problems of confinement that I'll get to later. All these techniques supplement the calculations in perturbative QCD, and those calculations have gone through amazing transformations in the past 10 years. In the past, basically, the automation of doing the traces, the amplitude calculations, so that for many processes, the next to next to leading order calculations of QCD have been done. And for 2-to-2 processes and jet processes, the next to leading order plus the next to leading log summations have been done. And using techniques based on cutoffs in the jeticity of higher order diagrams, these results can be replicated in more and more calculations. So the calculation of higher order QCD diagrams in QCD perturbation theory will continue to be a very active and very rewarding field, because these processes are seen very clearly. Multi-jet processes are seen very clearly in collider physics. Spectroscopy amplitude analysis helps us get down to the low energy regime where we think we are approaching the things that are of interest in nuclear physics, and certainly nucleon-nucleon amplitudes have been studied quite carefully in terms of potential models in order to turn into a nucleon-nucleon potential that can be used in nuclear physics. But these potentials don't seem to have any traction with what we understand from QCD. So I'm going to be talking in more detail later here about one particular type of experiment, which is semi-inclusive deep inelastic lepton scattering, where you scatter off of a proton and you catch at least one hadron in the final state along with the scattered photon. And the reason why these are important for these studies of proton structure is that these kind of experiments can be analyzed in terms of transverse momentum-dependent distributions and fragmentation functions that allow us to get a three-dimensional picture of the proton structure, not just the longitudinal degree of freedom that's measured by Bjorkane X, but also the KT dependence of the rest of the structure. And here's a sketch that includes something like a Feynman diagram for the single photon scattering off of a quark, allowing for maybe a gluon to be radiated in the final state, and a nuclear target, and you collect something like a meson out in the kinematic region where you expect it could come from the fragmentation of a quark, or something with baryon quantum numbers, which would signal that it connects with the diquark quantum numbers of the remnant particles left behind after you take out a quark. And the thing that allows us to do a three-dimensional analysis based on these studies is that there are three independent planes defined in this process. One defined by the target, and if the target is polarized, then we know that if we have an asymmetry, it can only occur in the momentum on the transverse plane transverse to that. And similarly, if we measure a spin observable in the final state, it can only occur in the green plane. So the dynamics of this. And when you talk about tomography, you realize that you always, in order to discuss the interior of an object, you need an axis. Like on the Earth, we always draw maps with the north up because the world is rotating around that. And if you took a bunch of maps randomly oriented at different times and different directions of the North Pole, you would just have a mess that showed you that there was some land and some water, but you couldn't tell where they were. So it's only the kind of maps that are oriented that make sense to study internal structure, and that's why spin observables, and particularly transverse spin observables, are very valuable in doing the calibration for all of the other observables that we can define in deep inelastic scattering. So orienting these planes, so obviously if I flip the spin of the proton, I flip the orientation of the blue plane, and I flip the spin of the final state particle that's polarized, I flip the orientation of the green plane. So those things are to be kept in mind. I've already talked about this. What I'm saying is that transverse spin observables provide a very special tool to address the problems that can help guide us to the answers we need to confront the issue of confinement. And so one of the things I'm going to understand is the idea that there's orbital angular momentum inside a proton, even though it's supposed to be an S-wave configuration of 3 quarks, is very important. because that's something that isn't expected to be there. But it's hard to imagine a confined system where things don't go around in orbits, right? So, and what I'm going to show here, that the fact that the pion is the lightest mass particle, and a pseudo Goldstone boson that is important in the understanding of dynamical chiral symmetry breaking, also tells us something about mechanisms that can produce internal orbital angular momentum inside of a proton. And basically you see over on the side something that indicates that you can resolve a valence or a constituent U quark with spin up into a down quark with a current down quark, which is almost massless, and a pion. So you've taken something that has mass of about 1/3 of the proton, and you resolved it to something that's light and something that has a mass of about a tenth of the mass of the proton, and then there's about 2/10 of the mass of the proton that can be used up in orbital angular momentum in that process. So the virtual transitions of that sort might be something that actually generate orbital angular momentum. I call the fact that the vacuum, a quark-antiquark pair that's produced in a 0++ state, in other words, has vacuum quantum numbers, has to be in a state where the two spins, so this is a Q bar, are down, and there's orbital angular momentum normal to the two spins. And this it can occur in any orientation, but this is a very strong kernel for the breaking of chiral symmetry in the vacuum. So the vacuum itself has chiral properties. When I produce QQ bar pairs that have vacuum quantum numbers, they have to be oriented and produce orbital angular momentum. And if that happens, if that kind of virtual transition happens inside of a proton, as I say, it produces something orbiting around the direction of the proton spin, and that orientation creates a blue shift for the quark coming towards you of 1/10 of a Bjorkane X, and a red shift on the other side of 1/10 of a Bjorkane X. So it matters where the quark is when you scatter off a deep inelastic scattering. The scattering tends to occur at one point, and then the fact that the quark that's now suddenly changed direction is going out is attached to the rest of the proton by a force. The force that kept it orbiting, kept it confined, translates into an asymmetry. So we've shown a mechanism related to chiral symmetry breaking that I call the pion tornado that can generate an asymmetry in the production of a jet of particles out of a polarized proton. I want to also tell you why this idea of triplet P0 virtual pairs, which can be produced by a gluon, by the way. I mean, so these are essentially nonlinear or non-local things. But they're something that have shown to be present. And one of the ways you can see they're present is there are two images of a delta that people have discussed. One, which was discussed by the quark model people like Dallas and Harry Lipkin, that it was 3 constituent quarks standing in attention, all with their spins in the same direction. And the other one, which was proposed by very clever people, Jack Uresky and Stanley Mandelstam, and codified by Jeffrey Chew, is it's a quasi-bound state of a proton and a pion in an L wave. And when you did N over D, you find that this partial wave saturates unitarity, and which basically means it's even money. If you look at a delta, which you'll see, whether you'll see the three quarks standing at attention or a pion nucleon state, and that just tells you that in quantum field theory, vacuum quantum numbers are very special. And this is why lambda 5/4 theory is trivial, and why if you're going to look for a non-local effect, it helps to look first at the vacuum state, because when you fluctuate something in a vacuum state, it's the equivalent of everything else fluctuating the opposite way. But if you fluctuate something like a gluon or a quark fluctuation, you have to have another one. You have to have another one either locally or somewhere else to balance. So it's, if you're going to do an effective field theory, the first thing you do is put in something that called the nonlinear sigma model to mimic what happens with the vacuum kind of quantum numbers. And here's a cycle that a delta can go through before it decays. It can spend some time with three quarks bound together, and then it can produce a pair and go back. And this is what the N over D equations tell you is the dominant thing that happens during a delta particle's lifetime before it finally falls apart into a nucleon and a. So it's interesting to look at the quantum orbital dynamics and spin-directed momentum transfers that happen from confined non-abelian systems. And one of the reasons it's interesting, and I alluded to this, but I'm now going to do it in a more direct way, just like in perturbation theory, if you start with zero masses, you can't generate mass from perturbative diagrams. If you start from perturbation theory, you can never generate a single spin asymmetry from light quarks. And all of these diagrams are always proportional to the mass of the quark over square root of s. And as you saw, the mass of the up and down quarks are very small. And we believe in quantum field theory, in QCD in particular, you can do calculations with massless quarks, and those are legitimate because it's just it's a small extrapolation away from the physical masses, and the pole, what are called the pole masses, and the mass parameters are running parameters, and so you can take them to zero and still do valid calculations. And then if you take the mass of the up and down quarks to zero, you have a real extra symmetry of the perturbation theory, which I've called artificial time reversal, and Bob Jaffe calls naive time reflection. And basically, it's a symmetry which changes the sign of axial vectors while leaving the sign of vectors unchanged. So it's the dual of the parity operator. And if you do that, obviously all single spin asymmetries are odd under that operator O, and the product A tau is parity times that operator, which can be called the snake operator because it replicates the Siberian snake that Derbrnev and Kontratejko invented. They invented a way of changing the spin of a particle without changing any momenta. And so here are the symmetries that are that can be used to talk about doing physics beyond the standard model that are sensitive to single spin asymmetries. So I talked about, I was going to introduce the work that Professor Ralston and I did. And we were looking at that time on understanding the QCD vacuum in terms of a background field approximation. So we looked at a formulation that was spherically symmetric of the fields for SU2, which is a way of embedding SU2 into a sphere. I'm going to talk about a variation of that where instead of using spherical coordinates, I use cylindrical coordinates. But the basic techniques that we modified from other people who are doing similar things with instantons and things are preserved in this. And so if I introduce spherical coordinates and I introduce them both in SU2 space and in physical space, I introduce tensors that have both 3-space and SU2 indices. And so I'm working in a adjoint representation of SU2 for the purpose of this demonstration. And the point is I can always, if I rotate this system around the z-axis, I can always use a gauge transformation to rotate the red tensor, the red things, while I rotate the blue things. So any rotation around the z-axis can be compensated by a corresponding rotation of the SU2 space. And therefore, and if you start with the ansatz for the gauge field like this, you'll notice that there are a big A0 and A1. So I'm going to have an abelian theory along the z-axis, and the transverse degrees of freedom will take care of the nonlinearities of the SU2 thing. And so if one of the things is to look at the covariant derivative at the bottom, dAB of a vector along the z direction that has a gauge, and that turns out to be using the A above written by that equation, and it introduces a rotation of the two directions by an angle omega. And if I take the commutator of that covariant derivative with the z itself, it produces an orthogonal thing. So I've now introduced a gauge-dependent set of tensors to do my gauge derivatives in. And that was the thing that John and I came up with. And that we can project the covariant field strengths, gauge covariant field strengths on this basis. And then we have the definitions of the longitudinal E field and the transverse E field, and we have the longitudinal magnetic field and the transverse magnetic field. And you see that SU2, like its higher order brother SU3, has a non-abelian topological current. So these fields, these transverse fields, can be expressed in terms of a current, which has a derivative which is E dot B traced over the A's. Okay, so I can plug this equation into the equation for the transverse degrees of freedom, or I can just leave it there. And notice how that equation simplifies if I set the longitudinal magnetic field to 0, and so it vanishes, and then the terms on the left vanish, and and everything simplifies. And the non-abelian Maxwell equations are then quite simple. And the Bianchi identities that give the further constraints, and there's a requirement of covariant current conservation. So when I said A equals 1 and I let the longitudinal magnetic field vanish, I can define a confined system where I said A equals 1 for out to a certain radius of this cylinder, and then have it change direction down to A equals -1. And then I've defined a cylinder where I have E dot B not equal to 0. And that cylinder is a topologically stable thing. This is a soliton kind of solution. So it has stability characteristics which are insensitive to small variations of the fields around that. And at the outside, I can fix everything to be 0. All of the phases and everything vanish on the outside, and that means I have a confined system where the only QCD fields can exist are inside. And so this is a model of a jet in QCD, a rapidly expanding system with cylindrical symmetry in the quenched approximation, where I don't have any.
Time for a question.
Sure.
So you're building. I need the other slide.
Aha! I was trying to get past that other slide.
So you're building a flux tube.
I didn't build it.
You've got a lot of ansatz here.
Of course, yes. Okay, so I built it.
First, are all the sources 0?
No.
Or is there? Do you differentiate the heck out of the Yang-Mills equations and then compute the source?
No.
I can't tell.
Yeah, the sources are given up there.
Is it the J0 and J1?
Yeah.
Okay, so.
And that just tells you that the gluons are colored.
Any Yang-Mills, I can write down any configuration, differentiate the heck out of it, and come up with some currents. So what's special about this particular configuration?
It's topologically stable.
Now,
So I can take variations around that.
You talk about the topology. Is the topology the same as an ordinary flux tube topology for a U1 theory, like a type 2 superconductor? Is it your real topology around the periphery of the tube?
The periphery of the tube. So here's a redrawing of that where I've done a cutaway. So I have only electric field in the core of the tube. It's like a coaxial cable. I have complicated QCD fields spiraling around, and then everything goes to 0.
And then is there one rotation around the tube? When you go around the periphery of the tube, you have one gauge?
Yes, it is completely continuous around there, and
so that's what makes it a topological flux tube.
that's what makes a topological flux tube. And and here's a better. So this is. So by going from 1 to -1, I have to go through 0. And that means that there is a ring of dions. There is zeros in this thing, and in our form, 0 is the equivalent of a thing that has an electric and magnetic charge. So it's and there is an area where the topological current has a derivative that's non-zero. If I'd done the same thing in the spherical coordinates, I'd get the same answer. a range coming out and then a topological shell now completely enclosing the sphere. And that topological thing is again CP odd. And hence cannot, in condensed matter physics, they have things called topological insulators, which are things of putting insulators with topological properties like this inside of things that carry current. And so this is just the inverse of a topological insulator. Everything outside is nothing, and we have something that can constrain all of the fields inside of a shell. So I believe, and this is something which does not appear in perturbation theory, but it is something that has been seen in lattice simulations of quenched QCD, that they get areas surrounding the fixed charges that are CP odd. But they don't see it in such clarity because they work on a 4 torus with complicated boundary conditions. Using these equations, I can sketch the solution of a dressed quark with 3 of color that's coupled to an antiquark, and a scalar diquark with 3 bar of color that's coupled to a quark, and an axial vector diquark. And these, you can find approximate solutions to these field equations that where the two things can be separated by a certain bit, and you can find adjoint charges that have an 8 of color and are either symmetric or anti-symmetric in the color indices, and an 8 of color that are either symmetric or anti-symmetric in the spatial indices. These sketches are done in what's called the maximally abelian coordinate gauge, where T3 and T8 are diagonal. And that means that only off-diagonal fields carry R yellow bar, yellow blue bar, and B red bar of charges. And here's how you do the extension to QCD in terms of embedding 3 SU2s into the equation with the constraint. And I just wanted to say there is something that's classical, which is, has anybody seen a big cruise ship tied up with a hawser rope? These big ropes that are consist of 3 smaller ropes wound around each other. Now, if you take a hawser and you put it under tension, there is a lot of energy stored in that rope as it expands. And sometimes, like in a hurricane or a very strong wind, when a ship is blowing offshore, you have to cut that rope to keep it from damaging other things. And you see, if you take the Z enantiomer of the hawser and you tried to cut it this way, you would probably only hit the red strand, and you'd cut that, and then things would sort of go wild. But if you want to cut it, you want to cut it along the length of the rope, where you cut all 3 strands at the way. And if you're standing on the right-hand side and wielding an axe on the S enantiomer, you want to cut that way. And then if you do it on the other one, you want to turn around and cut that way. Because when that rope is done, the S enantiomer at the bottom will fling to the right, and the top will fling to the left, and vice versa as that thing. So this is to point out that classical physics has a lot of examples of things that store up this kind of energy that can be released in a rupture. And we're talking about QCD flux ruptures. That this is an example of how there can be a polarizing fragmentation function of a gluon. And that introduces the idea of spin-directed momentum transfers. I don't know how much time I have left, so I
can tell you, you have 10 minutes.
10 minutes. So I talked about, I mentioned that deep inelastic semi-inclusive scattering is a very instructive thing to do if you want to look at the quark and diquark structure of a proton, including the orbital angular momentum. And in particular, when you measure a spin asymmetry, you take a proton polarized up, and then you catch the number of particles that go to the left and the number of particles that go to the right. And then you turn it around and do the same thing. And so the difference between the number that go to the left and go to the right with the spin up should be the same as the difference that go to the left and the right, but opposite the other way. And so you can characterize the difference between those two observables in terms of either what I call an AN, which is the difference in terms of the numbers, or the difference in momentum space of the two curves locally. And also for a final state polarization, you can do the same thing. You can characterize the difference between a counting experiment in terms of a momentum shift, because that's the only direction that the momentum could shift. And we use that fact when we do experiments to minimize the errors, what do you call it? The non-statistical errors, the systematic errors. So characterizing what happens inside of a proton, these spin-directed momentum shifts are very valuable tools that characterize what happens, and they can be evaluated in terms of Wilson loops. So if I have the proton spinning in the up direction, and I scatter off a quark, and the quark goes out, then I would have the blue Wilson loop that could be calculated to give the kick that measures this observable. And if I had a pion coming in with the antiquark annihilating that thing and turning into a photon, I would have the red Wilson loop evaluating that. And you can see that if you sum over all of the locations of that possible event, that the sum over all red loops has to be the opposite of the sum over all blue loops. And that's the thing that John Collins proved to be the fact that the single spin asymmetry generated in semi-inclusive deep inelastic scattering has to be the opposite of the asymmetry generated in the Drell-Yan event. That I call that Collins conjugation. But it's most clearly viewed in this momentum shift, and also this momentum shift helps you understand how these things evolve under QCD evolution, because these momentum shifts do not change under QCD evolution, but the slopes of the different curves do change, and in particular, in particular, as you go out to larger and larger KT, the shape of the curves change from being a Gaussian to an exponential to a power law. And so the value of the counting experiments do evolve, but the momentum shifts don't. Now, it's interesting that in our understanding, the same arguments that lead to this idea that asymmetry in Brillouin is opposite the asymmetry in semi-inclusive deep inelastic scattering have to do with the difference between initial state interactions and final state interactions. But we have a more direct experience in if the primary thing that's carrying the orbital angular momentum is this quark-diquark system, then when the quark is scattered, the thing that's holding it back is the diquark. So the transverse momentum that's generated by this final state interaction on the quark is at least partially conveyed to the momentum shift of the diquark. The rest goes to other possible constituents. But that leads to the expectation that if we measured baryons in the final state of a semi-inclusive deep inelastic scattering event, we can predict the sign of the asymmetry by already knowing the sign of the asymmetry for an up quark or a down quark that goes to pi plus or pi minus. And so along with my collaborators, I have made those predictions. And there's also the possibility that the diquark itself had orbital angular momentum when something came out, and that shift turns into now the production of a polarized particle in the final state, because if it's a diquark with its spin pointing up and it forms a sigma plus, then it has to catch a particle with its spin down, and therefore the asymmetry of sigma pluses should have a large component of that, and that has been shown to be the case. If I measure, but in proton-proton collisions, if I measure the polarization of lambdas and the polarization of sigmas, and I assume that all of the polarization comes from effects in the final state jet, I get a ratio of -1/3 between the two polarizations. The rest of the polarization of the sigma has to come from what I call the fractured Bohr-Mulder's effect, the effect that is generated in the distribution of the unpolarized proton itself by correlating the orbital angular momentum with the spin of the diquark. And so if these things are measured in semi-inclusive deep inelastic scattering, we can measure the dotted curve and the difference between the dotted curve and the total thing separately, because we have the extra degrees of freedom, and we can confirm that the polarization of the lambda is produced entirely in the fragmentation process. So this is the power of semi-inclusive deep inelastic scattering. It lets us get deep inside the tomography of both the initial state proton and the final state jet. And both things are confined systems where we have these non-local events that involve orbital angular momentum. So, and the fragmentation of a diquark is very much like the fragmentation of a quark at first rank, but in its second rank, what happens to the next meson in line after you produce a baryon depends on either the isospin or the spin of that baryon, and can be predicted. And so you predict higher order 2 two particle effects in fragmentation based upon the understanding of the spin dependence of fragmentation process. And this is indicated in this kind of diagram. This has been observed in the Collins functions in E plus E minus, namely the Collins function for producing a pi minus from a U plus is large and opposite to the Collins function for producing a pi plus from a U quark. And that's representative of what we're producing, what we're predicting here for the Collins functions for producing various combinations of mesons after you produce a certain hyperon. And you can also take any time in Alice or CMS, anytime you measure a lambda, if you can orient its spin and then look at the particles around it in rapidity space, you can predict that there will be quantum number fluctuations that to the right or left of the particles from the generated by the polarization of the sigma zero. And I've shown some of these, and people are looking for them at Atlas. So I hope I've explained how going to non-perturbative ideas can be done in a controlled way in QCD, and experiment can lead us to further understanding about the kind of operators we need to discuss the interior. And I think taking into account confinement and topological properties helps us understand the pion cloud. And the pion cloud is not a cloud in the calm sense that you saw last night while you're watching the occultation of the moon. It is a tornado. The coupling involves a gamma 5, and therefore it involves some orbital angular momentum.